This video is sponsored by CuriosityStream. Get access to my streaming video service, Nebula, when you sign up for CuriosityStream using the link in the description. For centuries, humanity has used the stars to navigate our own world, but our future is to navigate to those stars and the worlds around them. We were deep into the holiday season this week, and I remember when I was a kid there was a lot of media attention given to trying to find or backtrack the location of the Star of Bethlehem, or Christmas star, mentioned as guiding the Magi in the Gospel of Mark. There have been a lot of theories advanced as to what that might have been, star, comet, nova, and so on, but it stuck in my head as a kid, having taken up a deep interest in astronomy, that the stars move relative to each other and us. Our sky changes slowly, but it does change, some of it cyclically, some of it not. It's something folks often don't appreciate about trying to send a ship, or even a message, to another star. If you aim for it, it won't be there when you or your message arrive. Today we'll be looking at interstellar navigation, but for completeness, we won't just look at slower than light travel today, but also faster than light navigation issues, and intergalactic navigation issues, and even problems with popping forward or backward in time through a wormhole. But even without time travel, the galaxy shifts a lot over time, and not in the regular and repeating way we see in solar systems. While objects do orbit the galaxy, much as moons orbit planets and planets orbit stars, there's very little recurring pattern to this. The Earth has orbited the Sun over 4 billion times, and the Moon orbited Earth probably about 50 billion times, and each orbit is nearly identical to the last. But our Sun has only orbited this galaxy about 20 times, and the galaxy never looked vaguely the same between each orbit. A few of the stars near us have been since our Sun's beginning, co-moving from the original nebula they all formed from, but many have been swept out of that pack and some have migrated toward us, while many more are just passing by at different angles, and were not our neighbors a million years ago and won't be in another million. The Alpha Centauri system is well known as the closest one to us, but its 3 stars are not siblings to our Sun, which is nearly a billion years younger. At the moment, our solar system is moving in the general direction of Altair, the 12th brightest star in the night sky, 17 light-years away, but what we mean is that we're moving toward its approximate current location at 26 km per second, which is still less than 1% of light speed. So don't worry, we won't hit it, not even close, though our Sun has often passed near other stars. Everything about the interaction of stars in this galaxy can be thought of as very temporary, at least in the timescales of a star's lifetime, not like the patterns of planets and moons. Altair is rather young, just over 1 billion years old, but it is one of the bigger types of stars, an A-type nearly twice our Sun's mass, and will turn into a white dwarf well before reaching our Sun's age of 4.6 billion years. Both our Sun and Altair orbit the galaxy roughly every quarter billion years, so they both already completed several orbits, but many giant stars won't even live 1 billion years and won't live long enough to complete a single orbit. Even a ship capable of near light speed, you can't just aim it at a star and expect to arrive there, because you're looking at old light the star emitted tens or hundreds of thousands of years ago, and you'll see the star moving along as you get closer to the newer light. Because you're looking at the old light the star emitted tens or hundreds or thousands of years ago, and you'll see the star moving along as you get closer to the newer light. Of course, you would try to predict the star's trajectory and plot an intercept course, but remember the star isn't in a simple elliptical orbit like a planet around a star. It's on a complicated trajectory affected by all the other stars that will pass anywhere near it during that millennia of your travel, so you'll have to project the motion of all those stars as well. In other words, you'll need to model the motion of an entire section of the galaxy, so let's hope you have the data and processing power to do that. And while you're at it, make sure you won't encounter any poorly timed supernovas and that the star isn't going to be dead when you get there. You often hear people talking about navigating by pulsars, and that's both a very good and also very limited means of navigation. First, we should clarify that a pulsar is not exactly a unique star category, but rather most are fairly recently formed neutron stars, and are visible as pulsars from certain angles and during their more energetic youth. All neutron stars are produced by a giant implosion of a bigger star, most of which is blown away in a supernova, but the explosion occurs in the middle layers of that star, so it pushes the outer layer away, exploding outward, and the inner core gets pushed inward, and the implosion forms a hyperdense chunk of superhot, degenerate matter. This is effectively a dead star now, but it retains all the heat energy and all the angular momentum it used to have before getting crunched, and it gains even more heat energy during that implosion. Stars generally rotate on an order of days to months, but angular momentum is the product of mass, radius, and velocity, and is conserved. So when the radius crunches down 1,000-fold, the velocity goes up 1,000-fold, and since the object's radius and circumference are 1,000 times smaller now too, the rotational rate will jump 1,000 squared, or 1,000,000 times faster. Pulsars can vary in rotational rate from as little as a few milliseconds to several seconds, but each pulsar is pulsing at a very specific rate and spectrum, essentially a unique signature, the one that changes with time as the pulsing is taking up a lot of energy, and the neutron star produces no new energy, just what it has in terms of heat and rotational energy. This pulsing is also not omnidirectional, coming off the poles of the star, so is not visible as a pulsar from all angles. Thus, even though we estimate there are over 1 billion neutron stars in our galaxy, we've only detected a couple thousand. We suspect there may be 100 times that many not yet detected, but that still means not even 1 in 1,000 neutron stars is a pulsar, or at least is one anymore. The Crab pulsar in the Crab Nebula about 600 light-years away is one of the few optically visible pulsars, and believed to be the remnant of the supernova SN 1054, recorded by Chinese astronomers in 1054 during the Song Dynasty as a guest star. It's only 1,000 years old from our perspective, the star having died several thousand years ago, but we are seeing it as it was when the light left. That's the thing to remember though, if you traveled there now, it would seem to age very quickly as you approached, especially if you were jumping there by warp travel of some sort. Its current period is 33.5 milliseconds, or 33.5 million nanoseconds, and it is slowing down. Its period increases by an estimated 38 nanoseconds a day, or 0.0139 milliseconds a year. So if you suddenly fell through a wormhole to arrive nearby it, you wouldn't find it at that 33.5 millisecond rotational rate, you'd find it at something more like 120 milliseconds, because it's 6,000 years older now that you're closer and has slowed a lot. As I said, there's estimated to be over 1 billion neutron stars in the galaxy, and most would have been pulsars at some point. But we figure on only about 1 in 10,000 of them being visible as pulsars, and have only detected about 1 in a million of those neutron stars as pulsars. This isn't just a distance issue, some of the known pulsars aren't even our galaxy. It's a time issue. They just don't stick around that long, and those pulsars in other galaxies aren't going to look even vaguely the same if you jump there, assuming you could even detect one. Nor can you assume that a neutron star is slowing at a precise and constant rate over thousands of years. Any absorption of mass, for instance, can alter a neutron star's characteristics, and they are often formed in places where a lot of material is floating around to be absorbed. Indeed, most of our heavier elements in the universe are the products of neutron stars merging with other neutron stars, rather than a dying star exploding. Key thing here is, while pulsars are a great way for figuring out your location during relatively mundane interstellar travel, it won't help you for getting hurled through vast amounts of space and time by some entity or anomaly, as we often see in science fiction. You don't get chucked halfway across our galaxy, even to the same point in time, which is a pretty dubious concept anyway, and just check your local pulsars for a quick positional fix. They won't be where they were on your map, they won't be spinning at the rate you expect, and they won't have the same spectral characteristics. Given time to find all the local pulsars and get a fix on the galactic center, the Andromeda Galaxy, and so on, you'll be able to guess your location decently, but this won't be fast and it won't be precise. And it isn't something just fixed by having way better computers. If we are talking about getting hurled into other galaxies or any motion in time, then you're pretty much out of luck with pulsars. However, that still leaves them good for local navigation, right? Sure, but in basically the same way stellar navigation is handy for getting around town. You can do it, but it's both overkill in terms of effort and way less precise than just using a map, let alone a GPS with a map. Pulsars are great for local interstellar navigation, but aren't really necessary because you aren't going to just suddenly pop out of somewhere on some unknown trajectory if your spaceship is operating under known physics. They'd be handy for getting a fix if you whacked some bit of space debris and your ship was in a tumble and lost lock and it took you so long to restore everything, like years, that you couldn't just grab an image of the starscape from right before the accident and tilt the ship that way and be back on course. That could plausibly happen to an interstellar sleeper ship whose computers got damaged, and some backup protocol woke up the ship's pilot and navigator. In general though, the sheer amount of energy available in any given solar system, and the sheer amount of energy needed to run an interstellar ship's engines, is so massive compared to the energy needed to broadcast an omnidirectional radio signal folks could hear for a few light centuries around, that you would expect every single star system we visited to have at least some automated transmitter that just sat around watching some radioactive isotopes decay and shouting out the time and its identification number and the frequency it transmitted at. You pick up the signal and it says it's 104.9 FM and 8:45 AM December 17th, 2020, and yet you're picking up on 103.8 FM, telling you the frequency redshifted 1.06%, and that you are moving approximately 3,000 kilometers per second away from the transmitter, or 1% of light speed, your radial velocity. You can then look at your own clock and compare the dates for the actual distance. If you can pick up a few more, then you can triangulate your position very accurately and way better and faster than by pulsar. It is just GPS, only the G stands for galactic, not global. It's also important to understand that while the exact method, ID, and names might vary over galaxy-wide civilization, if you're all traveling slower than light, you are going to have decades elapsing between times you need to worry about potential alterations of such a system, and plenty of time to be contacting nearby systems for updates and news on any major changes on navigational systems. And these sorts of calculations can be done easily and near instantly by modern computers, but also fairly quickly manually, and there's nothing high-tech about picking up a loud radio signal and doing some trigonometry and redshift calculations against some catalog of local stellar nav beacon IDs. And given the time it takes to travel, you could literally raise a child from infancy and hand them the manual on how to do it, and still have plenty of time to make your corrections. You are also not too dependent on any given system either. Space is three-dimensional and wide open. If your ship can pick up the default navigational beacon orbiting the average star from a few hundred light years away, then you should have many thousands of beacons to pick from. Even if some can't be bothered or they're automated and several fail, or even if some intentionally tamper with their beacons to screw people up, you shouldn't have a big problem getting a fix. And when in doubt, you can be using pulsars or other things too big or cosmic to fabricate to confirm things are about right. You can also enforce beacon trustworthiness and function fairly easily too. As an example, Earth is likely to be the effective center of the galaxy for a very long time, at least to humans, not just the center from which colony ships emerge, but the place where most of the research is getting done, and where most colonies probably had an embassy to make sure they got that new technology. It would be very easy for Earth to say they will send a signal containing tech data only to beacons transmitting the right date, time, and transponder code. Odds are pretty good that it would be a fairly standard protocol for neighbors too. The one type of interstellar commerce we can be confident will be common and large in content is the transmission of information at light speed. I cannot see neighbors cutting off all transmission if a navigational beacon went offline or screwy, but that information is money and power. It might even be digital people transmitting copies of their own minds. So you are probably not transmitting that to some system that went haywire on transmission and navigation protocols, and no system has a motivation not to have plenty of backup beacons online. They are not that power hungry. A gigawatt radio signal can be heard many light years away easily enough, and a gigawatt might be a lot to us now, but it would barely run an interstellar spaceship of the most modest sort. It also is not that much to us either. We have plenty of power plants in that energy range, and we might not use the entirety of one for a SETI signal, but we sure would if it was a central piece of our markets and economy. In all probability, it would actually be lower power than that though, with lots of megawatt or even kilowatt beacons scattered through deep space too. There's always the question what you're navigating around, because it is, at sublight speed and under known physics, pretty hard to miss a star if you started off aimed in the right direction. And yes, they do move and quickly too, but even if for some reason you didn't calculate that into your original trajectory, it's not going to be that hard to track as it goes. Rather, you will probably be navigating around and tagging all the minor bodies in deep space. Interstellar navigation is mostly tricky for all the tiny junk in space, and we'll be talking about millions of minor planets per solar system and trillions of things too big to vaporize or allow for the ship to absorb the hit. I would tend to guess that most systems that were decently developed but still hadn't totally consumed all the natural raw materials in their ore clouds would probably leave radar array beacons on every minor planet they found to inform folks not just that they existed, but to sweep the area for space debris and let the ships know about it, much akin to the role of lighthouses or buoys marking shoals. This is another reason we never talk about stealth in space. It is really hard to hide ships when everyone who needs to deal with spaceships also needs to deal with pebble-sized nuclear bombs, because that's the kind of energy an interstellar spaceship is going to receive as a blast if it runs into a pebble no one detected, and it's the kind of energy any pebble-sized bit of garbage lost by that ship is carrying if it runs into a space station or planet. I know we all like to think of the future in space as a peaceful place, but don't ever assume that means it's demilitarized. A developed star system is going to offer a lot of things to visitors and traders, just about anything they could be looking to find, and if they're looking for trouble, they're going to find that too, because your typical K2 civilization, just one lone star system, even a pretty low-tech one with no fancy sci-fi science, could beat the snot out of most of the fictional galactic empires we see in sci-fi. We'll talk about that more next week, but short form, you're listening to all those navigational beacons less to find your position and speed precisely, which you can of course, and more to make sure you don't do anything that is going to cause any of the tons of telescopes around that system pointed at your spaceship to tell any of the tons of automated weapons platforms to point your way to. That's the first rule of warfare after all, don't pick fights you don't have to, especially with people bigger than you. The nature of interstellar spaceships is one where you've got potentially megatons of ship moving at speeds where each kilogram of that ship amounts to a nuke, and very little time for contemplation or chat. Warning messages are things a ship's captain pays attention to because warning shots do not exist, and if some megaton space freighter moving at 10% of light speed into a solar system veers off the accepted course and deceleration pattern, the next thing it finds along its new and unauthorized trajectory is likely to be enough ordnance to level a continent, because that's the kind of kinetic energy it is carrying if it hits something. So what about the classic sci-fi case of your ship getting thrown through a wormhole or some other anomaly and emerging in an unknown place, or even an unknown time? Ignoring that our current knowledge of physics says that probably can't happen, how would you figure out when and where you were? Well, the first thing you'll be doing is settling in for a long wait, and one probably long enough to move your ship to the nearest star system to be picking up raw materials for construction, because this won't be fast. The first thing you would want to do is start pinpointing galaxies and their redshift away from you. You might get lucky and find you are in or near your own galaxy and fairly close in time, but you can start estimating your own speed. You probably did not emerge at relative stop, by the speed of those local galaxies relative to you. Their distance from each other and relative speeds to each other can give you a good hint where you emerged in time too, because everything in the universe is expanding away from everything else, in general, and the rate and average distances will tell you a lot about time. So too will the frequency of the cosmic microwave background radiation, or CMB. We tell people that CMB is at 2.7 Kelvin, or more precisely 2.72548 Kelvin, plus or minus 0.00057 Kelvin, and that's the peak wavelength. It is a spectrum. It also varies a bit by direction you look, that plus or minus being those cold and hot spots you see on the CMB maps of the universe, variations of less than 0.02%, and corresponding to a frequency of about 160 GHz or 1.9 mm wavelength in the microwave range of the spectrum. That is for today, when the universe is about 13.8 billion years old. It was at a much higher frequency when the universe was younger, since those little photons weren't microwaves when they were made. They were in the visible or high infrared range, and have redshifted around 1,000-fold in their interim journey. So if your spaceship pops out of some anomaly at an unknown point in the universe, and you measure the CMB at about 4 or 5 Kelvin, not 2.7 Kelvin, you know you have plenty of time to find your way home, because you've popped out of space-time to about when the Earth was first forming. Alternatively, if the CMB is colder, you know you've gone ahead in time and can calculate by how much. How precisely just depends on how precise you can measure the CMB from your ship, how good your civilization's measurement in your computer archive is, and how solid your model of the universe expansion is. I gave it to about 6 significant digits, so that's presumably what we could do now, and should let you pin down your date to within a range of 100,000 years of this general era of the universe. If you emerge trillions of years in the future when the CMB is down into the radio range, not microwaves, you'd be looking at estimating to hundreds of millions of years, and another big clue will be that you will either find no galaxies, or just one very big one, as by about 1 trillion years from now, galaxies will all have coalesced with their neo-gravitationally bound neighbors, while the others have all done the same with their neighbors but expanded so far away they fell over the cosmological event horizon, leaving you in a volume of space essentially vastly bigger than the current observable universe, but with only one single large galaxy, which may be dying off by then, star formation generally expected to begin ebbing around the trillion-year mark and finishing off well before a quadrillion years. If you're further ahead than that, and assuming you had awesome sensors, you could be guessing the age still of that CMB as it redshifts ever further and also off of black holes. They are expected to evaporate and give off energy over truly long periods of time. See our Civilizations at the End of Time series for a discussion of surviving in this era by forming those black holes. However, if you can sample a lot of them for their mass and Hawking radiation rates, you should be able to guess decently accurately, relatively speaking, about how old they all are. Your margin of error for this, even if very small, is likely to be a period of time longer than the current age of the universe. You also might, if your sensors are high-tech enough, be able to pick up telltales of the gravitational waves given off by black hole mergers, which are monstrously energetic events even compared to supernovae. Or for that matter be able to pick up neutrino background radiation from the very beginning of the universe. The CMB all originates from when the universe was about 300,000 years old, what we call the last scattering, as before then the universe was so dense photons generally got absorbed rather than wandering through light years of space. But neutrinos would not have been absorbed, and should have a CMB equivalent that we could use to look at the earlier universe even before the last scattering if we get better at neutrino detection. Could you figure out where you were though? Well, maybe. There are some very large objects in the universe in a nebulous sort of sense that are pretty unique. And if for instance you have mapped out the various cosmic voids, you would probably be able to calculate a decent idea what their size and shape was when they were younger or older, and match that to your time estimate for the universe to figure out which voids you were seeing were which ones in your archives. So too, quasars are monstrously powerful and visible universe-wide, and you might have good luck calculating position off those if you can make good guesses as to which were which. Of course, when I say universe-wide, I mean the observable universe, and that will be different if you magically teleported to a different piece of it, when or where, as we assume the actual universe is much bigger, maybe even infinite. See our episode on alternate realities and parallel universes for more explanation of that. In such a case, you might not ever be able to get your where, but you could still get your when, unless you win a different universe, not just a different part of it. In the end, if you get lost in space, you probably ought to follow the same policy when getting lost on Earth. Sit still and listen for a bit, to see if you hear anyone or someone saw you and comes looking, or head for the brightest source of lights or noise. In this case, that's just going to be a star or Dyson sphere, or galactic core, or some galaxy-scale megastructure like a Birch planet maybe, or just some random star that is closest and looks promising as a possible colony. Patience is a virtue if you're getting lost or traveling in interstellar space, and doubly so if you're getting lost in interstellar space, let alone intergalactic space-time. You might need to park your spaceship at some planet, terraform it, and wait 100 generations till you've got the skill, knowledge, manpower, and infrastructure to figure out where and when you are. The road to space is going to be a long one, and before we can navigate interstellar space, we first have to build up our presence in interplanetary space. As we often discuss on the show, asteroids are likely to be a focus for much of that buildup, in terms of mining them and settling them, and that begins with exploring them. At the front line of that exploration is the OSIRIS-REx probe, our asteroid hunter, and there's an excellent video on OSIRIS-REx over at our partner and sponsor, CuriosityStream. CuriosityStream has thousands of fun and educational videos, but they have also partnered up with us at Nebula, our Streamy Award-nominated streaming service, to offer nebulous content along with their own, if you sign up with the link in the episode description. That means you will not only get CuriosityStream and at a 26% discount, but also lets you catch SFIA episodes early and without ads, and help support our show while you're doing it, as well as see our exclusive Coexistence with Aliens series and other great content from our sibling shows. Again, you get a year of both CuriosityStream and Nebula for less than $15, get to support the show and see our episodes early, and get all of that for less than $15 by using the link in the episode's description. So we're almost done with 2020, but we still have a couple episodes and a live stream to go. Next week, we will look at how we go about building our own solar system up into a Kardashev 2 civilization. Then on Sunday, December 27th, we will have our monthly live stream Q&A. And finally, we will wrap the year up on December 31st with Becoming Interstellar Species. If you want alerts when those and other episodes come out, make sure to subscribe to the channel. And if you'd like to help support future episodes, you can donate to us on Patreon or our website isaacarthur.net, which I'll link in the episode description below, along with all of our various social media forums where you can get updates and chat with others about the concepts in the episodes and many other futuristic ideas. Until next time, thanks for watching and have a great week.